Hey everyone, welcome to Math 104. We're working on sections 7.1 and 7.2 today on radical expressions and rational exponents. Please start with a warm-up. We're reviewing the properties of exponents. So we're multiplying, we're going to add those exponents together. So that's x to the 7th. We're dividing, subtract the exponents. 6 minus 4 gives us x squared. We got power to a power here. Going to multiply those exponents. 4 times 3 is 12. So we get x to the 12th power. Now make sure you can do all of these in your calculator. Square root of 49 gives us 7. Third root of 64 is 4. And the fourth root of 16 is 2. So we're studying radicals today. I want to start with the definition of radical. So here's our radical expression. Let's say the nth root of some number is b. Another way of writing that is b to the nth power is a. So here's the anatomy of a radical. The index is the number here to the left of the radical. So you got, if you don't see a number, it's assumed to be 2, so that'd be a square root. And we have third roots and fourth roots. And then this is the radical symbol. And the number underneath the radical symbol is called the radicand. So we need to look at a few different situations that can arise when evaluating roots. And the first situation is when n is even and the number underneath the radical, b, is positive. So here's an example of that. We could do the fourth root of 81. And if we put that in the calculator, you're going to get 3. And that positive value is what's known as the principal nth root of b. And that's always going to be the positive version you can get out. So if we have the fourth root of 81 equals 3, another way of writing that, this version would be 3 to the fourth is 81. But that's not the only number that we can take to the fourth power to get 81. We could also do that with negative 3. Since we're multiplying it 4 times, we get 4 negatives, and the negatives cancel in pairs. So we'd have 2 pairs of negatives which cancel each other out, leaving us with a positive value. And that's what's known as the negative nth root of b. So the symbol itself without a negative sign, this is always the principal nth root, and that's always positive. If we want the negative version, we're just going to put a negative out front, find the principal, and multiply it by a negative 1, and that's the negative nth root. Now if b is a negative value, and n is even, you cannot take an even root of a negative value, so no real roots there. And then we've got the situation where n is odd, and that's easier. So let's say we got maybe a 5 under here, or 3 or something like that. Then we just get one number out, and that's the one real nth root of b. So the only situation where it's a little tricky is this one. So just remember the difference between the principal and the negative nth root. So let's take a look at an example over here. We want to find the principal fourth root of 256. All right, so we're going to find that fourth root of 256, and the positive version then is 4. And if we want the negative version, we do that fourth root of 256, we get 4 and multiply it by negative 1. So there is negative 4. Short number 1. Find the fourth roots of 16, both the principal and the negative. All right, there's the principal, fourth root of 16, the positive version, that gives us 2. And then the negative, put a negative out front, and get negative 2. Now next up, we're going to see a situation where we have to include the absolute value when we evaluate a root. All right, so go ahead and use your calculator to evaluate these two. So the square root of 6 squared and the square root of negative 3 squared. So a lot of people look at roots and powers as being opposites of each other. Kind of the way addition and subtraction are opposites, or multiplication and division are opposites. But it's not exactly true. It doesn't work all the time. So if we get this, starting on the inside, 6 squared is 36, square root of that is 6. So we're right back to the value underneath it. So in this case, the power and the root really do cancel each other out, leaving just the number 6. But here, negative 3 squared is positive 9, square root of 9 is positive 3, as the principal square root of 9 is positive 3. So it doesn't work for this one. We don't get the same number out. So the power and the root are not opposites of each other in this case. So in this case, we need a little different definition. All right, so the meaning of the nth root of a to the n, right? So if n is even, then the nth root of a to the n is the absolute value of a. You have to eliminate any negative under there. All right, if n is odd, then the nth root of a to the n is indeed a. For example, we're going to simplify these. All right, so fourth root of negative 5 to the fourth power. So n is even, all right, an even index. So that means we have to use this version. So the nth root of a to the n is absolute value of a. So this would be the absolute value of negative 5, which is 5. All right, so what we get here is if we took negative 5 to the fourth power, we get positive 625. Fourth root of that is 5. B, we're going to get the seventh root of negative 5 to the seventh power. Remember, this property only works if you have matching, if you match the power with the index. All right, now this is the second case. N is odd, so that means the nth root of a to the n is just a. A is negative 5, so this would be negative 5. And finally, for C, we're going to find the negative sixth root of negative 5 to the sixth power. Now this one here, we have an even exponent and index. So this would be negative. We have to use this one, so the absolute value. So it would be negative absolute value of negative 5. Remember, this negative, we have to keep that here. And that equals negative 5. And that brings us to your term number 2. All right, so this one, fourth root of negative 3 to the fourth power. It's the even version, so we're going to get the square root of a, or sorry, the absolute value of a, which is, Keep that negative sign out front. Absolute value of -3. All right, this is +3, but it's negative, so we got -3 there. All right, this one, another version of the n is even. So this is going to be the absolute value of a. So absolute value of -3, which is +3. And for this one, all right, we're going to use the n is odd version. So the nth root of a to the n is just a. Here a is -3, so we get -3 for that one. All right, next up we're going to be simplifying expressions with rational exponents. All right, rational exponents, exponents that are fractions. Fortunately, they work exactly the same way as exponents that are integers. So we're going to use the same rules for exponents, and in your packet, see a listing of all the rules for exponents that we've seen before. And now we're going to apply them to situations like this. We have x to the 2/3 times x to the 1/5. All right, so we're multiplying, as we saw in the warm-up, we're going to add those exponents together. So we get x to the 2/3 plus 1/5. Now we need to combine these, so let's find a common denominator. We need to have a denominator of 15. So this can be written as x to the 10/15 plus, and then 1/5 is 3/15. All right, now we have a common denominator, so we can add them together and we get x to the 13/15. Your turn, number 3. X to the 3/4 times x to the 1/6. All right, add the exponents. So we get x to the 3/4 plus 1/6. Now we'll find a common denominator. That'll be 12. So this will be x to the 9/12 plus 2/12. Add them together and we get x to the 11/12 power. Next example, x to the 2/5 divided by x to the 3/10. So when dividing, we're going to subtract the exponents. That gives us x to the 2/5 minus 3/10. Now find a common denominator of 10, so multiply this by 2/2. That gives us x to the 4/10 minus 3/10. Subtract those and we get x to the 1/10 power. Your turn, number 4. X to the 6/7 divided by x to the 3/14. Subtracting the exponents, we get x to the 6/7 minus 3/14. Now we get a common denominator of 14, so we'll convert this to 12/14 minus 3/14. And that is x to the 9/14. Next example, we have x to the 2/5 times y to the 3/7 all to the 1/3 power. So recalling our properties of exponents, we are going to apply the exponent to all bases inside the parentheses. We'll apply it here and here. We're doing power to a power. That means we have to multiply the exponents. So this gives us x to the 2/5 times 1/3 and y to the 3/7 times 1/3. Multiplying those out, and we get x to the 2/15 and y to the 3/21. I believe I had a misprint on mine. This was supposed to be 4/7 here. That makes this 4 and 4. That brings us to your turn, number 5. We've got x to the 1/2 power times y to the 2/7, all to the 3/5 power. All right, we'll apply this to both bases. Power to a power, we're multiplying the exponents, so that's 1/2 times 3/5 on the x, and the y 2/7 times 3/5. Multiplying those out, we get x to the 3/10, y to the 6/35. A more complex expression this time. We got x to the 1/3, y to the 2/5, to the 6th power over y squared. Sometimes we'll mix fractions and integer exponents. All right, I'm going to apply this to both of them inside the parentheses. Here we got 6 times 1/3. 6 divided by 3 is 2. So that is x squared. And here we got y to the 2/5 times 6. 6 times 2 is 12. 12/5. Y to the 12/5 there, all over y squared. Now to simplify, we'll combine any matching bases. So here we go, y to the 12/5 over y squared. Now we're going to subtract those two exponents. So we're going to do 12/5 minus 2. 2 can be written as 10/5, so that's really 12/5 minus 10/5, which is 2/5. So we get x squared y to the 2/5 power. Your turn, number 6. Start off by applying the exponent to both bases inside the parentheses. We'll do 1/5 times 15. 15 divided by 5 is 3, so that is x to the 3rd power. And then over here, we've got 2/3 of 15, which is 10. So that's y to the 10th power over x squared. All right, now we got matching x bases here, so we'll subtract those exponents. 3 minus 2 is 1, so that gives us x, and then y to the 10th. X, y to the 10th. You need to be ready for anything now. We're going to throw some negative exponents in there. So we need to think back to chapter 4, what strategies we use there. And so when we encounter problems like this in chapter 4, we'd start by simplifying inside the parentheses first. Right, we're going to apply properties of exponents here. Got some matching x bases here. So 3 minus negative 2 is positive 5. So that's x to the 5th power. And here we're going to do y to the negative 4 minus 1/5. So 4 can be written as 20/5. We're going to subtract another fifth, so that's y to the negative 21/5. And all that is still to the negative 1/2 power. Now the negative power, we can now apply that to each of these individually. All right, we're going to power to a power and multiplying the exponents. So that gives us x to the negative 5/2. We multiply 5 times negative 1/2. And then over here, multiply these exponents. So the negatives cancel, and that gives us negative 21/10. Oh, sorry, positive 21/10. All right, now finally to simplify, we're going to take the negative exponent, move that to the denominator, and make it positive. So our final answer is y to the 21/10 over x to the 5/2. Your turn, number 7. And all of this then is to the negative 2 power. So I'm going to start by simplifying inside the parentheses. 3 to the negative 1 power is the same as, in the denominator, is the same as 3 to the 1st power in the numerator. So I'm going to move 3 up there. All right, now we can combine the x bases. So here we have, we're going to subtract these exponents. Negative 1/4 minus negative 2 is the same as negative 1/4 plus 2. So that gives us x to the 7/4 power. And now we're going to combine the y's. We have negative 3/2 minus negative 2/3. We need a common denominator of 6, so the first fraction turns into negative 9/6. Subtracting negative is like adding, so we'll convert that to adding. And this is 4/6. So that gives us negative 5/6. So we have y to the negative 5/6 power. And we move this out of the denominator, we combine those fractions, we don't have a fraction anymore. So all those are gone. All those end up in the numerator. So we just write it like that, and we have to the negative 2 power. Okay, now apply negative 2 power to each one of these. So that gives us 3 to the negative 2. And then x, power to power, multiply the exponents. So that turns into negative 7/2, and we multiply 7/4 times negative 2. And then here we got negative 2 times negative 5/6, so that's going to be a positive 5/3. And now finally we can just move the negative exponents to the denominator. So on top, all that's left is y to the 5/3 over, right? And this goes to the denominator. Exponent becomes positive. 3 squared is 9. And then here we got x to the 7/2. So y to the 5/3 over 9, x to the 7/2. All right, next up, we've been looking at all these expressions with fractions as exponents. So we're going to see what that really means and then make the connections back to the radicals that we started with. So a fractional exponent, here's the definition, x to the m over n. So we have some fraction. Okay, the top value, that's always going to be the exponent. And the bottom value here in the fraction becomes the index of the radical. So we can write this in radical form, where that bottom value is the index. And then the top value stays as the exponent on the base. All right, so these two expressions mean exactly the same thing. And then there's one other way we can write it as an alternative. X to the m over n equals nth root of x, and then put the exponent on the outside. Right, these two things mean the same thing, and they both mean this. So a fraction exponent is just another way of writing a radical. All right, let's use this then to evaluate 8 to the 2/3 power. So I'm going to convert this to radical form. 2 stays the exponent, 3 becomes the index. So it would be the 3rd root of 8 squared. All right, now we can evaluate here. So that becomes the 3rd root of 64, and the 3rd root of, remember this is the principal 3rd root of 64. Oh, no, my bad. Odd exponent, there's only one root. So 3rd root of 64 is 4, and we're done. Your turn, number 8. If I evaluate 27 to the 4/3 power. Bottom number is the index. Use the other notation here. And there's a reason for that. It's actually easier to evaluate the 3rd root of 27 and then take it to the 4th power than to do the reverse. If we take 27 to the 4th power, we're going to get a gigantic number. So who wants to deal with that? All right, 3rd root of 27 is 3. So we get 3 to the 4th power, and that is 81. All right, now we're going to convert exponential expressions to radicals. All right, so the numerator of the rational exponent becomes the power. The denominator of the rational exponent becomes the index. So we're going to write as a radical expression 6 to the 1/5. Right? 1 becomes a power, we don't have to write it, it's implied. And 5 becomes the index, so the 5th root of 6. Your turn, number 9. Right, 2 to the 1/7 as a radical. 7 is the index. 2 to the first power, we'll just write that as 2. 7th root of 2. All right, now we're going to write 5 times x to the 2/3 power as a radical. Now, the exponent only applies to the x. It does not apply to the 5. So the 5 has nothing to do with converting this to a radical. The 5 is just going to stay on the outside. Now we've got the 3rd root. And 2 is the exponent. So that converts to 5 times the 3rd root of x squared. Another way of writing that, you can write it as 5 times the 3rd root of x all squared. Either one of those is fine. Your turn, number 10. Eight x to the 3/4 power. All right, exponent only applies to the x, so the 8 stays out of it. We got the 4th root. Denominator becomes the index. 3 is the exponent. 8 times the 4th root of x to the 3rd power. And you can write it in that form as well. All right, next example. 6x to the 3/5 power minus 2x to the 4/5 power. All right, over here, we got the same situation we did here. 6 is not involved in the exponent, so that stays out front. And then we've got the 5th root of x to the 3rd. Minus, now this one's in parentheses. So that means that exponent applies to the entire expression. So we're going to do, I'm going to use the other method over here. And inside we get the 5th root of the entire expression, 2x. 2x has to go inside the radical then. Your turn, number 11. All right, the exponent applies to this whole expression, so that's going to be the 8th root of 3x to the 3rd power. So you can write it like that, or like that. And on this side, do plus 4 times the 3rd root of x squared. All right, next example, we've got a negative exponent. So we're going to refer x to the negative 5/7 power. All right, negative exponent means this needs to go into the denominator. So we get 1 over x to the 5/7. And then we'll convert just like we did before. So that'd be 1 over the 7th root of x to the 5th power. All in the denominator. Your turn, number 12. x to the negative 2/5 power. If you move that to the denominator and make the exponent positive, and we get 1 over the 5th root of x squared. All right, now we're going to do this in the reverse. We're going to convert radical expressions to exponentials. All right, so to convert this, we're going to create a rational exponent with the power as the numerator and the index as the denominator. Nested radicals become power to power, so if you see those, we're going to convert the innermost radical first, and then we're going to apply the properties of exponents to write that resulting fraction in lowest terms. So let's see how that works out with a few examples. So we're going to write the square root of 7 to the 6th power as an exponential. All right, now we have a square root, so the implied index is 2. So that's going to go in the denominator. So we get 7 to the 6 over 2 power. Now we can simplify this. 6 divided by 2 is 3, so that is 7 to the 3rd power. And just leave it as that because we want to write these as exponentials. Don't have to evaluate it. Next up, your turn number 13. Write the square root of 9 to the 8th power as an exponential. All right, again, applied index is 2. So that gives us 9 to the 8 over 2 power. 8 divided by 2 is 4, so that is 9 to the 4th power. All right, next example. We're going to write as an exponential expression. We got a couple of them here. So we got 4th root of x to the 3rd times the 5th root of x to the 1st power. Now to combine these, first thing we do is convert to exponentials. Then we can use the properties of exponents. So this becomes x to the 3/4 times, and this is x to the 1/5 power, right? The implied power here is 1, and 5 is the denominator. So x to the 1/5. All right, now we can use the properties of exponents to simplify. So we need a common denominator of 20. All right, x to the 3/4 plus 1/5, and that is x to the 15 over 20 plus 4 over 20. Converting both to have the common denominator of 20. Combining those together, we get x to the 19/20. Your turn, number 14. sixth root of x to the fifth times the third root of x squared. All right, we'll convert to exponentials first. 5, the power is the numerator. 6, the index is the denominator. X to the 5/6 times numerator, denominator. X to the 2/3. So properties of exponents, x to the 5/6 plus 2/3. Now we need a common denominator of 6, so I'm going to convert this fraction. So x to the 5/6 plus 4/6 as x to the 9/6 power. And then we can reduce this fraction to lowest terms, which is x to the 3/2 power. Next example, we have the fifth root of x to the third power times the third root of xy squared. So we'll start here. 3 is the numerator, 5 is the denominator, so that's x to the 3/5. And this one, the base is xy. So we'll keep that in parentheses. And now, the denominator is 3, the numerator is 2. So that is xy to the 2/3. All right, now we're going to simplify this expression using the properties of exponents. So we'll apply the 2/3 exponent to both the x and the y inside here. That gives us x to the 3/5 times x to the 2/3 times y to the 2/3. Now finally, we're going to combine the two x bases into one. We're multiplying, so we add the exponents, that is x to the 3/5 plus 2/3 times y to the 2/3. Now we're going to add together 3/5 and 2/3. We'll need a common denominator of 15. So 3/5 turns into 9/15, and 2/3 turns into 10/15. Finally, combining these together, we get x to the 19/15 and y to the 2/3. That brings us to your turn, number 15. You have the fourth root of xy to the third power times the fifth root of x to the fourth. All right, here the base is xy, so make sure that goes in parentheses. 4 is the denominator, 3 is the numerator. So that is to the 3/4 power. And over here, we got 4 is the numerator, 5 is the denominator. So that is x to the 4/5 power. All right, now we can apply that exponent to both x and y. So that's going to give us x to the 3/4, y to the 3/4, times x to the 4/5. All right, now we can combine the x bases. Properties of exponents, we'll add those exponents together. 3/4 plus 4/5. And then we keep the y to the 3/4. 3/4 plus 4/5. We're going to need a common denominator of 20. So it gives us x to the 15 over 20 plus 16 over 20. Now we can combine those, 15 plus 16, that gives us x to the 31/20ths, y to the 3/4. All right, now I've got this really wacky looking thing here. 7th root of the 4th root of x. So we can start by converting the inside to an exponential. Keep that outside radical, 7th root of, and this becomes x to the 1/4 power. Okay, now we can convert this whole thing so let's consider this to be the base. X to the 1/4 power becomes the base. And now we're going to create a fractional exponent out of this radical. All right, let's consider this thing to be just one thing. All right, so it's x to the 1/4 to the 1st power. So that's how you should think about this. So we've got a 1 exponent here and a 7 here. So that becomes x to the 1/4 to the 1/7. All right, the 1/7 comes from the 1 exponent on the outside here and the 7 from the radical. Now we have power to a power, so we're going to multiply those two together. 1/4 times 1/7 is 1/28. So that becomes x to the 1/28 power. Your turn number 16. We are going to convert the 5th root of the 2nd root of x to the 3rd power. So let's start with that inside. In the 5th root, this becomes x to the 3/2 power. Right? Consider this to be x to the 3/2 to the 1st power. Right? Now we can convert again. So we're going to have 1 as the numerator and 5 as the denominator. So this becomes x to the 3/2 to the 1/5. Right, now we have power to a power, so multiply those fractions. 3/2 times 1/5 is 3/10. So that becomes x to the 3/10 power. All right, that is it for today. In this section, we're building up those fundamental skills that are required to work with radicals throughout this entire chapter. All right, everybody, have a great day.